Hello. So if I have this
Yes, sir.
diagram and I said that the angle of incidence now in this case becomes a critical angle because it is the angle at which or for which the angle of refraction is 90 degrees. So here the angle of incidence becomes a critical angle. Please, do you understand? Hmm? So angle of incidence I becomes critical angle.
Yes, sir.
Now the angle of refraction now here becomes equal to 90 degrees. So angle of refraction here becomes 90 degrees. Please, do you agree with this one too?
Yes, sir.
So the critical angle as light moves from this medium M, the denser medium to air. This is A. Here is air, and there's a denser medium. So maybe move from water to air is the critical angle for this thing. So another medium, which is this thing, to A, will now be equal to sine I all over sine R. Sine I all over sine. All over sine R. This formula you already know it. So
Yes, sir.
you are going to get this should be equal to sine I. Sine I is now looking at sine I is the critical angle, which will be C. So this will be sine C. Sine C. All over sine 90. All over sine 90. So all over sine 90. Now, but you know sine 90 is 1, or?
Yes, sir.
But sine 90 is equal to 1. So this one now we are going to get this moving from A is equal to sine C all over 1. All over 1. But the refractive index at light move from medium A I've already done. However, the refractive index of a medium is normally defined as the movement of light ray moving from air instead to water. Normally, when you're talking about the absolute refractive index, it is normally defined as light moving from air rather into another medium. But in this case, we have light moving, sorry, not air moving, light moving from air to another medium. But in this case, we have light moving from a denser medium to air instead. And so now, if you want to get light moving from air to another medium, to that medium, then we are going to say light moving from air to another medium. We are going to use the reflexibility of light. So another medium will be equal to the reciprocal of this. So that will give us 1 all over sine C. 1 all over sine C. Do you agree?
But say you defined refractive index later, but you not defined it.
Is it last week I told you last week I'll be defining refractive index later.
Yes, sir.
So I thought I gave you a lot of this thing. So you can use the refractive index in terms of the ratio of what they call it, light moving, the ratio of light in medium A, what they call it, using the speed. You can use that one. I gave you a lot of this thing, what they call it, formulas, and you can use that one to define it.
Hey, that from less dense medium to a denser medium. That's what you omitted. But the
But the
it together to form the definition itself.
okay. So refractive index is normally defined as the movement of the what do you call it? The movement of what do you call it? Air moving the I don't know how to put it. The defined as the movement of light moving from air to another medium. That is how normally we define refractive index. Movement of light moving from air to another medium. Now we call it absolute refractive index. And using a refractive index, we are seeing that it is constant for that given pair of media according to the Snell's law. According to the Snell's law, you have a lot of ways you can define it. You can use the speed of light. You are talking about light moving from one medium to another medium. The refractive index is the ratio of the light moving from one medium to another medium. That is it. So you can use their speeds to define it. You can use their angles to define it. Just as the Snell laws does. You can also, there's really no definite definition to it. You can use enough what I've told you to define it, and you should be good to go. But normal, I'm just trying to say that when you talk about refractive index, you are normally talking about light moving from air instead to another medium. So when you want to use this, we are going to use the reversibility of light. So now, if refractive index is light moving from air into another medium, then using the reversibility of light, you are going to get 1 all over sine c. And so let's say the whole of this is representing refractive index. So we can come and get something like this. I just wanted to prove refractive index is equal to 1 all over sine c. I hope you get what I'm trying to say. Yeah, I'm trying to mean.
Yes, sir.
So it's just the ratio of light moving from one medium to another medium. And it is constant for the given pair of media. It's constant for the given pair of media. So you can relate them in terms of their speed. So the ratio of speed of light moving from one medium to another medium, then you can add is constant for the given pair of media. You can just write it that way. However, you can also look for a lot of distance. So that is it. So this is the relationship between this all over sine c, and I've explained it using the critical angle and so on and so forth to this point. And I use the reversibility of light according to reversibility of light, and I was able to get 1 over sine c. And I said, let this one represent the whole of a to m. It's still refractive index, so we are still going to get to this all over 1 all over sine c. Now let's do total internal reflection. I'm already explaining what total internal reflection is. I hope I've explained what it means for total internal reflection to occur.
Yes, sir.
Now, for total internal reflection to occur, there are some, what do you call it? There are some factors or some conditions that makes total internal reflection occur. Now, before total internal reflection occur, light must move from a denser medium to a less dense medium. That is condition number 1. Now, condition number 2, the angle of incidence in the denser medium must be greater than the critical angle. So, for instance, if we were to put figures to this, if at this point the angle of incidence here is 60, and for at 60 degrees we're able to get 90 degrees, then that means the critical angle is 60. Now, before we can be able to let this one move totally internally reflect, we have to increase the angle of incidence. Now, when we increase the angle of incidence to this point, now it ceases to be 60. Maybe now it becomes something like 70 degrees. Now you realize that the angle of incidence now here is greater than the critical angle, which was 60. Because when you now shift it to 70, definitely this one will move inside. And so here the angle of incidence now becomes greater than the critical angle. That made it 90 degrees. Please, do you understand this point too?
Please, you are baffled.
I said the angle of incidence before total internal reflection will occur. Number 1, the angle of incidence, light must travel from a denser medium to a less denser medium. I hope you can hear me this one. This one you can hear it.
Yes, sir.
Now, secondly, the angle of incidence in the denser medium must be greater than the critical angle. That was what I was explaining. Do you also get this one? Do you also get this one? The angle of incidence in the denser medium must be greater than the critical angle.
Yes, sir.
And so these are the 2 main factors that, or 2 main conditions that must be obeyed before total internal reflection will occur. And so when you have to consider this, and I've already explained all these things. Now, and that will make total internal reflection occur. So if you want to generally define total internal reflection, you can say that Total internal reflection occurs when light traveling from a denser medium to a less dense medium is incident at an angle greater than the critical angle. So you can define this thing, total internal reflection, to be that which occurs when light traveling from a denser medium to a less dense medium is incident at an angle greater than the critical angle. Please, did you get the definition?
Yes, sir.
Good. And we are going to talk about some applications of the total internal reflection. Now, it is using the cutting of diamonds. Diamonds are cut so that the light falling on them is totally reflected at various angles. That gives it the sparkle. So when you go to the diamond cutting, they use that principle. They use the total internal reflection principle that I may not be able to explain into details because I don't really have the technicalities as to how it is done. But that is how they cut it in such a way that the light falling on it is totally internally reflected at various angles. That gives it the sparkle. So you realize that diamonds give sparkle, and because of the way they cut it, and so they cut it in such a way so that anytime light falls on it, it's totally internally reflect. So when it totally internally reflects, it gives it that sparkle. I don't know if you get my point. Mm-hmm.
Yes, sir.
Uh-huh. Now, then you're also going to talk about the fish eye view. The fish eye view also, the eye view of the sea, the fish in the seas also use that same principle, total internal reflection. So if you have something like this, or let me use this diagram. If the fish is here, you realize it. If the fish is here, uh, uh, the fish also undergoes the total internal reflection when if it's seen outside. So when I hit this point at a certain angle, it totally internally reflects. It totally internally reflects this thing. That is a little bit I can say about that one too. And so it also uses fish eye view. Is also a typical example of what do you call it, the total internal reflection. Now then, we also talk about mirage formation. Mirage formation. I know you know mirage or mirages, anyhow you want to say it. Now when we say a mirage, you are trying to say that a mirage is an elusive and deceptive image which is normally formed on tarmac roads on a hot sunny day. Or in other ways, you can say that it's an image formed on the sea on a cold day as a result of total internal reflection. So there's an image that can be formed on the sea on a cold day, but when it is on land, you are trying to say it should be on a sunny day. I hope you are getting it. Normally, we are okay with the land because that is what normally we see. Some of us, we don't go to the sea, so the land we can easily relate to this. And let me just explain how the principle works. You realize that when you are going somewhere, I don't know if you go out, but normally when your parents are taking you to school or something, when you're moving in the afternoon in a car, and you realize that sometimes from miles away, especially when you're sitting in front, from miles away, you can see a pond of water in front of you on the ground, on the tarmac road or on the tarred road. When we say tarmac road, is a tarred road, normally on a hot sunny day. But as you get closer to it, the more it appears to be elusive. When you get closer to it, it appears that it's not there. Have you seen that thing?
I can attest to that.
Uh-huh. That is what we call the mirage. It's an elusive image. Sometimes it's a reflection of what do you call it, the clouds. That is why it looks like a pond or water on it. It's a reflection of the what do you call it, the clouds. You know how the clouds distance. So when it reflects, it looks like it's a pond of water or water on it, a pool of water. There are some instances too. It looks like a reflection of what they call some of the trees because of how maybe the angles are reflected and so on and so forth on the ground. And they also use that same principle. When light travels through various layers of light, through various layers in the air of different densities. And so we realize that when light rays is traveling from the top, at any point in time, the density changes. So the angle increases, the angle of incidence increases. So we get to a certain point whereby it totally internally reflects. Now, when it totally internally reflects, then we get that image formed on the hot tarmac road. Now, the hot tarmac road or the hot road now becomes the screen on which the image is formed. Do you get it?
Yes, sir.
Good. Let's solve some examples, then we are good. Next week, we are going to look at reflection at curved surface. Reflection at curved surface. We are going to draw some diagrams, the mirror and all those things, the images and all those things. We are going to do only that one next week. Then we'll do lenses. Then gradually we'll be going. So let's do some mathematics under this. Let's do some mathematics. Let's solve some 2 questions. Now the first question is, a ray of light is incident at 60 degrees in air. Are you writing? A ray of light is incident at 60 degrees in air. A ray of light is incident at 60 degrees in air. A ray of light is incident at 60 degrees in air. A ray of light is incident at 60 degrees in air. A ray of light is incident at 60 degrees in air. Are you writing?
Yes, sir.
So a ray of light is incident at 60 degrees in air to a glass plane surface. 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 Find the angle of refraction.
So please, angle of refraction.
Yeah, find the angle of refraction. Given the angle of incidence to be, given the refractive index of air to glass as 1.5. Given the refractive index, so given the refractive index of A to glass, then is glass. So the spectacles you use, I know if you wear spectacles, the spectacles you use, and as a result, the principle is refraction. The principle is refraction. So from air to into your glass, I use that principle, refraction.
You said the refractive index is what?
You said the refractive index is 1.5. The movement of air to glass is 1.5. So the question is a ray of light is incident at 60 degrees in air to a glass plane surface. Find the angle of refraction when the refractive index is 1.5. When the refractive index is 1.5. I hope you can do this one.
Yes, sir.
What did you get?
So please, I'm on it.
Okay.
43.7.
Is that you had what? 40?
3.08 degrees.
You had 33.
Yes, sir.
Supposed to be 35. Oh. So check your working well. So it will be the refractive index is equal to sine I all over sine R. You know sine I is sine 60 all over this thing. Sine R is equal to refractive index. But we are looking for R, so we are going to get sine R is equal to sine 60 all over 1.5. Then after finding the answer, you are going to get sine R is equal to 0.577. And so you find the what do you call it? The inverse of it. When you find the inverse of it, you are going to get 35.2. Do the check your calculations well. Do you get it? So it will be something like this: sine R, sine I all over sine R. Sine R. And you've been given I to be 60. So this will be sine 60. Sine 60 all over. This one will go here and this will come in because we are looking for this R. So we are going to get sine R is equal to this. And this we are giving the equation to 1.5. So it will be sine 60 all over 1.5 is equal to sine R. What are you getting? Sine 60 all over 1.5 is what? 0.577.
0.576.
576. So to find for R, R will be equal to sine inverse of this one. Sine inverse of this. That will be R. Use your calculator and see if you still get 35 on this thing.
So yes, I have 35.3.
So good. Now let's do another last question. The speed of light in air. 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 The speed of light in air and water. The speed of light in air and water are 3.0 times 10 raised to the power 8 ms negative 1. The speed of light in air and water are 3.0 times 10 raised to the power 8 ms negative 1 and 2.25 times 10 raised to the power 8 ms negative 1 respectively. I repeat, the speed of light in air and water are 3.0 by 10 raised to the power 8 ms negative 1 and 2.25 by 10 raised to the power 8 ms negative 1 respectively. Calculate the critical angle for water when light moves from water to air. Calculate the critical angle for water when light travels from water to air. Calculate the critical angle when light travels from water to air.
At least you've not stated medium one.
The speed of light in air and water are 3.0 times this thing. Calculate the critical angle for water from light travels from. Calculate the critical angle for water when light travels from water to air. The medium one will be the water to air or air to water, whichever way you are looking at it. So the speed of light, I told you this. So this is air, this is water. So this is medium one, this is medium two. And you are saying that the speed of light in air is 3 times 10 raised to the power negative times raised to the power 8. And that of this will be 3 by, what do you call it? 2.25. 2.25. So if you want to find for the speed of light, if you want to find the refractive index from air to water, the refractive index from air to water will just give you the speed of light in air, which is medium one, into speed of light in water. Have you gotten it?
Yes, sir.
So this will be 3 over, listen, all over 2.25. 2.25 times 10 raised to the power, and this will give us 1.33. 1.33. Now the questions that you should find for the refractive index of when light travels from water to air. So refractive index, as usual, that will be this will be sin C. Sin C is equal to 1 all over this one. So sin C. So you are looking for the critical angle. So the critical angle will be sine inverse of 1 all over this. And you know this one is 1.33. So the answer you get is your critical angle. So you get 48.
I had 50.285.
50.285. Sine inverse of 1 all over 1.33. What are you getting? Check, use the calculator again. Sine inverse of 1 all over 1.33. Have you found it? What did you get?
I said I did it to 1 decimal. Yeah, I had 48.75, but my own I did it to 1 decimal place. The three I did 1.3, not 1.33. That's why I had
Please.
this.
Okay, so do it 1.33. Normally, when you are working, let me show you one trick. When you're working, you don't want to get different answers. For instance, if this was to be the final answer, you could have just left it to 1.33. Are you getting it? But because after this, you also be using this value again. Don't leave it in just 1 decimal place. Leave it as it is and use it to do the final work. Did you get what I said?
Yes, sir.
If it is the final answer, you can run it. But if it's not the final answer, please use all the decimals so that it doesn't affect your final answer. Because sometimes the marking scheme doesn't give room for that. The person might think you're wrong. Meanwhile, you're correct. You get it? That was to be
Yes,
the
sir.
final answer. Then you could have just written the answer and run it so that the person would know, okay, you just rounded it. But if you are going to use it again for another step, then don't run it. Use all so that it doesn't affect your your work. Hmm?
Yes, sir.
Tomorrow, what do we have? We have commas, eh?
Yes, sir.
What are we doing? What are you doing in commerce? I don't know. What are you doing in commerce?
I thought you said menstruation or something.
Oh, okay. I'll go through. Yeah. Thank you. Have a wonderful day.
Please, I wish
Is it?
indices.
Yeah, we are done. We are done. We are done. We are done. And a commerce, we are done. So have a wonderful day. Bye.